Comparison of remote sensing indices and a temporal study of cienagas at Cienega Creek. I had two purposes. One was just to explore remote sensing indices in cienega habitats, and the other was to determine trends for cienagas. A quick overview of this presentation. One, what are cienagas? I will answer that next. Then study site, data methods analysis, and a few conclusions. Cienagas are specialized desert wetlands. They are sources of water in an arid landscape. As such, they are hotspots for biodiversity. They also are indicators of the general hydrologic function of the area. They also provide important ecosystem services, such as soil detention and flow modulation. Historically, as sources of water in an arid landscape, they've been heavily utilized. Grazing, irrigation, these things. Plus other factors, it's led to widespread degradation. More recently, cienagas have been recognized as sites for conservation. That leads me to my study site, which is La Cienegas National Conservation Area, which was established in 2000. It is managed by the BLM. It is one of the most extensive systems of cienagas, both historically and extant, in southeastern Arizona. Along with cienega habitats, Las Cienegas also protects a couple other interesting landscapes, Sacaton grasslands and cottonwood gallery forests. So you can see here, this is Arizona. This is the Cienega Creek watershed. Down in the southeast corner, zooming in, the Cienega Creek watershed, and these little blue blobs are the approximate locations of the cienagas. And this is Tucson, so Cienega Creek feeds into Pantano and then into the Santa Cruz. Zooming in even more, you have all of the cienagas visualized on this map. In order to do that, the cienagas are actually not in the same scale as the rest of the map. They're a little larger so that you can see all of them at once. It gives you a good general idea of the distribution of the cienagas across the landscape. These little inset maps are actual size, and, well, not actual size, but to scale. But it gives you a better idea of the diversity of size and shape. Looking here at Cinco Pond, you can kind of see how all of these blend together. And over here, you can see the diversity in size, Cinco Ponds being very large, relatively large, Cinco Pond 8, relatively small. But these were my study sites and my sites of interest. The data I used Landsat 5 thematic mapper imagery. A Landsat 5 sensor was operational from '84 to 2011. For each year, I pulled one scene from May, June months, and that's because May and June are the hot, dry pre-monsoon seasons. Any vegetation that has access to water should really stand out from the otherwise dead, dry, and senescent landscape. I also used a digital elevation model. The cienagas themselves were GPSed by Ron Tiller and Andrew Salawan in 2013. So my methods, I applied 5 different spectral indices. The first one, NDVI, Normalized Difference Vegetation Index, is the classic measure of vegetation greenness. It is a combination of red and near-infrared spectral bands. And it's really useful. Use it all the time in a lot of different habitats. It does have some drawbacks. One of those is it reacts counterintuitively to open water. It also has some issues with bare soil, especially in moderate vegetation covers, both of which happen in cienega habitats. Hence my interest in exploring other indices. Another vegetation index that I explored was the Soil Adjusted Vegetation Index, that's SAVI. It is basically NDVI, but with this soil adjustment fudge factor. Like, okay. And that's the L factor in that formula. I also explored a water index. This is McFeeder's water index. It's a combination of the green and the near infrared. I also explored 2 moisture indices or infrared indices. These are combinations of near infrared and shortwave infrared bands. Landsat 5 has 2 shortwave infrared bands, band 5 and band 7. So there's 2 separate infrared indices. I also looked at one topographic index. This is based on DEM data, 2 topographic parameters that are combined to determine sort of soil moisture potential. So I was looking at 28 years of spectral data, 5 spectral indices, and then the topographic index. Automation was key. And so I automated in Erdis Imagine with Spatial Modeler, also ArcGIS with Python, and I did my statistics in SPSS. So my first analysis, examining trends through time, I wanted to see how the index values were changing for each cienega through time. This is the Agfield pothole, and you can see all 5 index values changing over time. This is the water index down at the bottom. Apply linear regression. In the linear regression formula, this slope coefficient is what I used as my trend. Looking at the trends through time. These are the vegetation indices, NDVI and SAVI. This table is the index value trend through time plotted for each cienega. Now cienegas are roughly north-south, and so you can see there's a definite directional trend in there. So index values are increasing in the northern end and decreasing in the southern end. Right now we're looking at NDVI. We can look at SAVI. Generally similar values, but SAVI trends are a bit more moderate. The water index, also a directional trend, but opposite of the vegetation indices. Not that surprising considering the placement of the near-infrared band within the formula. The moisture indices, or the infrared indices, there's not a clear directional trend. There was high clustering. I did run a spatial autocorrelation on all of the indices, and they all were very clustered, but there's no clear directional trend. But the values are still pretty similar for both infrared indices. Here we're looking at the infrared index using band 5. Oh, there we go, band 7. Band 7 comes up with some more extreme values. My second analysis was to compare the indices a little bit further. And where I chose to go with that was to see if I could determine which index can distinguish cienega from upland or riparian habitats. So I created a sample design. I have those 44 cienegas GPS'd. I buffered the streams and excluded cienega, and that gave me a riparian zone. I was able to distribute 33 random points through that zone. Everything else I considered uplands. And I was able to randomly distribute 44 points through that. So I have these 3 groups. I know they're different. The question is, can the index pick up on that difference? And to examine that, I used an analysis of variance. I applied that to the topographic index and also the 28 years of the spectral indices, but all separate because precipitation and differences in rainfall could have complicated that analysis. So just looking at, for this scene, are they different? So the results for the topographic wetness index, ANOVA showed significant difference between groups. That's all ANOVA does. So I went to post hoc testing. The variances were heterogeneous, which indicated Tam-Haines post hoc comparison. So what the post hoc testing does is it says, well, group A is different from group B, and so B is different from C. So I wanted to get that. And what the post hoc showed is that upland means are different from both cienega and riparian means, but that cienega means are not different from riparian means. There's no difference between those groups, which to me means that TWI can't distinguish between cienega and riparian habitats. Going into the spectral indices, again, ANOVA, significant difference between groups for all indices, all years, except 1986. I had a hard time finding a scene in 86 that didn't have clouds. Didn't have that. The top of a cloud over uplands is kind of the same as the top of a cloud over other groups, so oddly enough. So excluding 86 from any further analysis, going into the post hoc testing, upland means were different from both Cienega and riparian means for all indices, all years. That's not surprising. I picked them from May and June so that that would be easy. The more interesting question is, what index can distinguish between the means of Cienega and riparian habitats? And for how many years? And that's what this table shows. And you can see the normalized difference infrared index utilizing band 5 was able to tell the difference between Cienega and riparian means for 16 out of the 27 years examined. That's about 60% of the time. And the other index values, reliability kind of dropped off pretty sharp. So just to review really quickly before my conclusions, now you know what Cienegas are. That's exciting. We went to La Cienegas National Conservation Area, just southeast of town, very beautiful. Data methods, analysis, and results. We've talked about all of that. And moving into conclusions. So the change in index values through time, there was a directional trend present in the vegetation and water indices. It's north-south, so that's latitudinal. But other things are correlated with that. The northern sites are also the lower sites. There's an elevation trend. The northern sites or the lower sites are the downstream sites. So you have a hydrologic trend. There's also a difference in canopy cover. The northern sites tend to have more trees within and surrounding the Cienega, and that could have affected these directional trends. Topographic index, TWI cannot reliably distinguish between Cienega and riparian habitats. That could be a resolution issue. If anyone ever flies LiDAR out there, TWI might get very useful. The spectral indices, the normalized difference infrared index using band 5 was the most reliable in distinguishing Cienega from riparian habitats. It was able to do so in 60% of the years analyzed, much more than any other spectral index I looked at. Therefore, based on the analysis, it may be more suitable than NDVI and should definitely be considered. And I'll leave that up while I take questions.